Okay, on the right-hand side of the board is where we left off last time in Chapter 3. We were looking at modeling conduction heat transfer by resistances called thermal resistances. There was a conduction resistance in a plane wall. T1 was one side of the wall, T2 is the other side of the wall, and so we then find the resistance, which is listed there, L over Ka. L over Ka. Heat flow is Q, that's the heat rate. If we have convection heat transfer on one of the surfaces of the wall, then we add this resistance, the convection resistance. 1 over HA, T surface, T infinity, free stream temperature, heat rate Q. And we combine those guys into series and parallel. We did one of these series, we did one of these parallel, and I showed you a series parallel combination like the typical wall construction of your home with inside wallboard, wood studs, insulation, and stucco on the outside. Or maybe it's a roof where you have plywood on the roof, roof tile on the roof. So that's, again, series parallel, convection on the inside of your attic, convection on the outside of the roof. The parallel one, I don't think I finished that. Here's the parallel combo. It's in your notes. But I don't think this got in your notes last time, so just make sure it's there. If this is a parallel combination of resistances, then RA and RB, then the way you find the heat rate Q, T1 minus T2 divided by R equivalent from DC circuits, 1 over R equivalent equal 1 over RA plus 1 over RB. If there's a third material in parallel, RC, then you have plus 1 over RC, and so on, and so on. If you want to combo these guys, it's RA, RB divided by RA plus RB. And of course the R's are over there on the right side of the board. So that should be added to your notes. Okay. Now, with this, there's one more that we can do. We typically, walls are very important for us. A lot of things can be modeled as plain walls. But of course, a lot of things can't be. And one of the most important things is if you've got a power plant from Edison or somewhere, steam power plant, you've got a chemical plant, you've got a petroleum refinery, you've got a solar collector field, you probably want to insulate some pipes carrying hot fluids. As a matter of fact, you do, an awful lot. So the next logical geometry, these are plane walls, is to model cylindrical conduction. Okay, so now, next topic, cylindrical conduction. Okay, I'm just going to show you, this is a typical, this can be a pipe. The outside radius can be R2. The inside radius can be R1. I'm assuming heat's conducted from the inner surface at R1 to the outer surface at R2, so just for argument's sake, heat's going from the hot inside to the cold outside. To find out about the temperature distribution in a pipe like that, this could be, for instance, a steel pipe, I'm going to take a small differential element in this pipe. Just like we played the game when we had a plain wall, or in x and y coordinates, we took a small differential element dx dy. When we work with cylindrical coordinates, we take a small differential element whose thickness now, what's the major coordinate? The radius. What's a differential then? dr, right. We take a little thin strip of the pipe like this, and that little thin strip of pipe has a thickness of dr. So this is the thickness dr. The pipe is length L into the blackboard. Into the blackboard the pipe has a length L. The diameter on the outside is 2r2. Inside 2r1. Now we take that little thin strip out. Let's put it over here. Here's the little thin strip. Here's the general radius r. The thickness of this is dr. And now we're going to run an energy balance on that. Okay, it's the conduction. We know it's conduction. So we have the amount of heat being conducted at this radius r, and the amount going out here, qr plus dr. We're going to assume steady state. We're going to assume no generation internally. We're going to assume constant properties. We're going to assume 1D conduction. Conduction is only in the r direction. 1D conduction. Okay, the energy balance. E dot in equal E dot out. Remember, there's no E dot storage, there's no E dot gen. What comes in is Q at R. What goes out? Q R plus dr. QR plus dr expanded in a Taylor series. Neglect higher order terms. There it is. Okay, look at the equation. QR on the left, QR on the right, cancels. We've got this guy then. dr. What is QR? Minus K A dt dr multiplied by dr. The circumference pi times r, pi times r, pi r. Diameter 2r. Area for conduction, circumference times the length, 2 pi r times L. Now this is, by the way, equals 0, 0, subtract. Okay, carry that through. This gives ddr. Divide through by the minus sign, divide through by the k, they're constants. Divide through by pi, divide through by 2, they're constants. ddr of r dt dr equals 0. If you want to, you can go back to chapter 2, the heat diffusion equation in cylindrical coordinates, and you can derive it also from that equation, chapter 2. Okay, there's a governing differential equation. Okay, we want to solve that for t as a function of r. Okay, so let's go ahead and integrate this guy once. R dt dr must be a constant, C1. Divide both sides by R dt dr C1 divided by R. Integrate it, natural log. Integral 1 over x dx is natural log of x, so t as a function of r equals C1 natural log r plus C2. Okay, notice that now the temperature distribution is logarithmic. Logarithmic. Okay, now next step. I want to get rid of C1 and C2. I need two boundary conditions. BC number 1. I didn't put it over here, I'll put it over here now. The temperature on the inside surface is T1. The temperature on the outside surface of the pipe is T2. Okay. So when R equal R1, T equal T1. BC number 2. T equal T2. If you put these guys in there, we did that for the plane wall. This is going to give the solution T as a function of R. So that. Okay. Logarithmic. Now we know what we did over here. Once you get the temperature distribution, now let's just go back over here for the plane wall. We solve that guy in the first part of chapter 3. Now if we go back to that, the first part of chapter 3, and let's see where we had that. Okay, there it is on equation 3.3. When we solve that with the right boundary conditions over here, this is what we got. Linear. So we drew a straight line from there to there. Linear. Over here, we're going to plot temperature versus the pipe radius R. Temperature T1, temperature T2. We start up here, temperature T1 when R equal R1. We go to temperature T2 at R equal R2, but it's not linear. Here's the magic words. It's got to be logarithmic. There's how the curve looks. It's a log-shaped curve. Major difference in a pipe and a plane wall. Pipe and a plane wall. Now, once we get the temperature distribution, like over here, here's what we do. We write the governing partial differential equation. We apply the boundary conditions to our initial conditions. We get the solution. Temperature as a function of whatever, X or R. The next step is find the heat transfer either through the wall or through the pipe wall. Over here, you want to find the heat transfer through the wall. There it is. We did that last time. Q equal T1 minus T2. I'm going to make that Q double prime divided by L over K. The heat flux. Okay, so guess what we do here now? We're going to find the heat transfer through the pipe wall. Okay, so through the pipe wall, QR as a function of the radius, K A dt dr. Fourier's law in terms of radius. Of course, the area now is different. There's the pipe wall. Okay. There it is right here. How's heat being conducted? Out that way. What area does it go through? The outside area. Circumference times length. Pi d times L. 2 pi RL. Okay, there's the area. Go ahead and differentiate this guy right here with respect to R. Okay? And we get 2 pi KL, of course, 2 pi KL right there. T1 minus T2 divided by natural log R2 over R1. Okay, so that is for pipes, or tubes, or any cylindrical, a storage vessel, whatever it might be. And someone said, you know what, that thing, looks somewhat analogous to Ohm's law that says that the electrical current is equal to a difference in voltage divided by the electrical resistance. This thing says the flow of heat is equal to a difference in temperature divided by, I'm going to call that thermal resistance. Okay. This is now R for a cylinder. And if you want to do this, like over there, then here is T1, here's T2, here's the heat flow Q, natural log R2 over R1, 2 pi KL. The heat transfer equation Q and the resistance that goes in that equation. So I'm going to put those equations over here by this guy, but before I do that, I want to go through this. Okay. What I want to do with this is I'm going to pretend that that wall is made out of copper, a really good conductor. Then it's out of fiberglass insulation. That temperature, I'll make something up. That temperature is 100. That temperature is 30. That L is 5 meters. If that wall's made out of copper, draw the temperature profile. Okay. 130. There's a temperature profile. Now, if that wall's made out of fiberglass, I change material dramatically. Draw the temperature profile. Wow, you know what? It didn't change at all. It looks the same. It's the identical line. Well, look at the equation. Do you see K anywhere in the equation? Of course you don't. So no matter what the material's made out of, the wall's made out of, temperature distribution is identical. You say, well, there must be some difference in the material. Oh yeah, there is. Look at the second equation. Do you see K? Oh yeah, big time. If K is big, Q is big. If K is small, Q is small. Copper, K is big. Fiberglass, Q is small. Oh yeah. There's where the material comes into all this stuff, in the heat flux. So yeah, it sometimes amazes people. They think, well, there must be a difference in the temperature profile for copper and fiberglass. The answer is, sorry, there's not. Same thing. Because the equation, K disappeared. Okay. Now let's not forget, all this stuff comes from chapter 3. Let's not forget, all the conclusions I've made depend on this. You must have assumptions of 1D, yes I did. Steady state, yes it is. No generation, yes it is. Constant properties, where? There was a K right here. I pulled the K, because it's a constant, outside here. Now I divide through both sides of the equation by K. That's why it disappears. That's why it disappears. K divided by K, 0 divided by K. Okay. So you won't find K in here with those 4 assumptions. Okay? But it's only good for those 4 assumptions. All these resistances are only good for those 4 assumptions. If you don't have those 4 assumptions, you can't model it by that resistance right there. All right, let me put here conduction in cylindrical geometries. Okay, so we have T1, T2, Q, natural log R2 over R1, 2 pi KL. What if we have convection in a pipe or a tube? Okay, here it is. It doesn't matter. It's the same equation for a convection, no matter whether it's a plane wall or a cylinder. It's the same equation for a convection. Where's the difference? In the conduction through the solid material, a pipe or a wall. Okay. All right, I think that's pretty much got what we need out of that. So let's go ahead now and take a look at using these in some problems. I'm going to work 3-6. For homework, you have 3-3. So I'm going to work problem 3-6. Oh, by the way, one last thing. A lot of times we engineers deal with, we're storing things in spherical containment vessels. So, yeah, we want to throw in, we're not going to derive anything. We're going to, for spherical geometries. See table 3.3. Okay, TRIES. R, like over here. They give all the R's in there for plane walls, cylinders, and spherical walls. 1 over R outside, inside minus 1 over R outside. Divided by 4 pi k. So you've got the resistance for a plane wall here, resistance for a cylinder, pipe or a tube here, resistance for a sphere here. Okay. All this stuff here appears in table 3.3. Okay. Back to 3.6. I'm going to read 3.6. There's a picture given, but I'm going to read through it anyway because it's a very hard problem to understand. As I told you before, many times these problems require you to read them 2 and 3 times because they're like real-world problems. And things don't automatically click from the first reading. Okay, here's what it says. In a manufacturing process, a transparent film is being bonded to a substrate, as shown in the sketch. So a transparent film is being bonded to a substrate. Here's the bond surface. To cure the bond at a temperature of T naught, so this temperature here is T naught. To cure it means to make it stick to the substrate. You want the film to stick to the substrate, called bonding. To cure the bond, a radiant heat source is used, providing a heat flux Q naught double prime. So you provide some radiant heat source up here, Q naught double prime. We're not given any areas, so everything's double prime heat flux. All the radiant heat is absorbed at the bond surface. All the radiant heat is absorbed at the bond surface. The back of the substrate is maintained at temperature T1. While the free surface of the film is exposed to air. Air blows over it. At temperature T infinity. Convection coefficient is H, between the air and the surface. There's 4 parts A, B, C, D. Part C and D have red boxes around them. We wouldn't do those for homework, the red box sub-problem. So we'll start with part A. The author says, show the thermal circuit representing the steady state heat transfer. Show the thermal circuit representing the steady state heat transfer. We can put it right here. JP, you okay down here? Okay. Okay. This is conduction through the film, through the substrate. We've got a resistance of the substrate, a resistance of the film, and a resistance of convection. Let's start the top, convection. T infinity. This is convection. Everything's on a heat flux basis. So 1 over H is the resistance. Now we go to conduction through the film. That conduction through the film has a thermal resistance of L over Ka. On a per square meter basis, it's L over K. So L over K. Now we go through the substrate. This is L of the film, K of the film. Now we go through the substrate. To what temperature? Temperature T1. The conduction resistance, L of the substrate over K of the substrate. Okay, there's our three resistances. Let me read this. I missed one thing when reading it. He says the free surface of the film is exposed to air. The free surface of the film is exposed to air, okay, and he calls, oh, there's right there. I got it there. That's T naught right there. T naught. So T naught is between the substrate and T1. Is right here. T naught. Okay. If you want to put one more in there, you don't have to. It didn't ask you for it. You can call that temperature T2. That would be right there, T2. He didn't ask you for it, so you don't need it. Okay. Now, let's see. I think we've done what he wanted us to do. Let me reread it. Show the thermal circuit and be sure to label all the elements. It says label the elements, the nodes, and the heat rates, and leave in symbolic form. Symbolic, no numbers, symbols. Label elements. The element are resistances. Labeled, labeled, labeled. The nodes, T infinity, T naught, T1. Okay, I'll label it T2 just to satisfy him. Now I've labeled all the nodes. And the heat flows. Okay, I got to label Q. Okay, now I read the problem again. I say, let's see, if I want to find, I'm supposed to find, let's see, part B says, find the heat flux. And we call that heat flux Q naught double prime. And I say, okay, so the heat flux comes in, it goes in by convection, then it goes through the film by conduction, then it goes through the substrate by conduction, and it ends up at T1 down here. That's what my arrow shows. Okay, I'm going to read it again. I'll tell you the key words. In a manufacturing process, a transparent film, there it is, transparent. A transparent film. If this glass were perfectly good glass, it would be transparent. I guarantee you, I see the leaves on the tree. I see everything out there. That's transparent. I look through the wall. I can't see a thing. The wall's opaque. It's not transparent. So what does transparent mean? It means the sunlight being reflected out there comes through this window to my eye. That film's transparent. Here comes the energy. Keep reading. A transparent film is being bonded. The heat flux that comes in, Q naught double prime, all of which is absorbed at the bonding surface. All of which is absorbed at the bonding surface. This Q naught double prime goes through the film and ends up where my finger is. Okay, now I know. If I read it 2 or 3 times very carefully and look for key words, now I know this is not right. No, the Q doesn't go there. Again, where does all that Q end up? Where my fingertip is. Okay, now we got it. Okay, there's the picture. Now it's drawn correctly. And I'll label this Q2, and I'll label this Q1. Because if all the heat comes in there, some might go out to the right, some might go out to the left. It depends on those temperatures.
You want to make those heat flux and so Q double.
Oh yeah, thanks, I do. Thank you. I sure do. Okay. Now, let's see what part B is. Okay, for part B, he gives us numbers now. Once you draw in the picture, he says T naught is T infinity is 20. T1 is 30. You have to get the bond surface up to a temperature of 60, or the film won't be bonded to the substrate. So he tells us T naught is 60. Oh, now we know which way the heat flows. Conduction, it goes from hot to cold. Hot, 60, cold, 20, right. Hot, 60, cold, 30, right. So now we know the energy balance. What comes in, Q naught double prime, must equal what goes out of the node at T naught. The node at T naught, energy balance on the node. Q double prime 1 plus Q double prime 2. Now he also gives us, let's put it up here. He gives us those dimensions. He says that, let's see where that is. There it is. 1/4 of a millimeter for the film and 1 millimeter for the substrate. K of the film, 0.025. Watts per meter degree C. K of the substrate, 0.05. Okay, got him. All right, now we're ready to go. Q1, okay, here's how we do it now. Q1, that goes to the right. We're going to do the same thing we did over here. Okay, right there. Take your two fingers, put them between the two temperature nodes. There they are. What's the resistance between my fingers? LS over KS. Okay. Hot temperature, 60, minus cold temperature, 30, divided by the sum of the resistances between those two nodes. LS, substrate, 1, divided by K substrate, 0.05. Yeah.
Shouldn't it be, okay, yeah. All right.
Okay. All right, and then plus, because here's Q2 now. All right, take your two fingertips. Between the two nodes, you know the temperatures. I know the temperature here and the temperature here. Okay, 60 minus 20. Divided by the sum of the resistances between my two fingertips. 1 over H plus the film resistance. 1 over H. H was given, but I don't think tell you yet. H was 50. H was 50. 1 over 50 plus L of the film, 0.00325. Yeah, 0.25 millimeters, yeah. Divided by K of the film, 0.025. And when you're done, Q naught double prime. Q naught double prime. Let's see where it is. There it is. 2833. Yep, 2833 watts. So it's I did it in class because that's a hard problem to understand. You try and draw the circuit, and sometimes people don't put that Q naught double prime in the right location in that diagram. It goes right here.
Is Q naught double prime usually generated by electrical means?
Do you have a rear window defogger on your car? Can you flip the switch on the dashboard and defrost the back window?
Yeah.
How does it do that, do you think? What do you think it does?
Yeah.
Does it blow warm air? Like in the front, on the dashboard, the front window, the windshield. When you defog that, what happens? Doesn't hot air blow up there?
Yeah.
Okay. Do you think the back window does the same thing? What happens back there? Did you ever try look and see what's in that glass? What's on the glass? Black lines. Yeah, black lines. You didn't put them there, right? No. Electrical wires.
Okay.
So when you flip that switch on your dashboard and you put a current through those wires, you're putting heat into what? The glass? Now, where does the heat go? Maybe it goes outside to the air outside the car, and some might go into the inside the car. There it is, your back window.
Okay.
You put electrical current in the glass gets warm, some air goes to the cold outside, some heat goes to the cold outside, some heat goes to the inside of the car, or maybe the inside of the car is hot and heat will flow from the inside of the car to the glass to the outside. So it depends on what's hot and what's cold. These temperatures right here, what's going to happen?
All right.
Okay. You wrap pipes up in the high desert with a solar collector. You wrap pipes around hot oil pipelines. In the morning, you trickle electrical charge through that electrical heating blanket to heat the oil. You hope most of the heat goes into the oil. You inflate the pipe. But some of the heat leaks out through the insulation too. And again, here comes electrical power comes in. Some goes to heating the oil. Some goes through the insulation out to the surrounding air up at Barstow. Okay, same thing. So it happens quite often, but that's what I'm saying. These problems require deep thought, and there are key words you want to focus on, whether it's homework or an exam. Focus on take a yellow marking pen, mark them out, key words. They'll give you major hints. You miss a major hint, that problem can be really difficult to solve for you. Okay, all right, now let's see. One last thing. We're going to work one last problem today, and that is something which is like your refrigerator in your kitchen at home. It's 3-7, next one, 3-7. Okay, this is a refrigerator. Let's see which one we got here now. Yeah, here it is. Let's read it, 3-7. Okay. The walls of a refrigerator are typically constructed by sandwiching a layer of insulation between two sheet metal panels. So when they build a refrigerator, it's supposed to be insulated, obviously. That's the idea. But you don't want bare insulation in your kitchen and you touch it and it just crushes, or anything. So you want to protect it by a thin panel, maybe a stainless steel refrigerator, whatever it might be. So here's how the panel looks, he says. There's a metal panel, there's insulation, and a metal panel. All right, so here's the insulation, K insulation, and here's the metal panel, K metal, metal panel, K metal. Of course, in your kitchen, there is air moving. There will be convection heat transfer. This is T infinity. I think I'm going to call that inside. This is the inside. There's also air moving inside the refrigerator. Not much, but there's enough to worry about. And this is T infinity on the outside in your kitchen. There is an H on the inside wall, and there is an H on the outside wall. Let's see what else. Oh, we know the distances. As far as the thicknesses of each of these three, the thickness of the insulation, 50 millimeters, and the metal skin on the inside and outside, 3 millimeters. Okay, now, that's our model of the wall. Okay, let's see what he tells us. I think he gives us some numbers. 3, 7. Yeah, okay, let's put the numbers down here in the margin. K insulation, 0.046 is fiberglass. K insulation, 0.046. SI units, watts per meter degree C. K of the steel panels, 60. KP, let's call that KP for panel. 60. We got, okay. L is 50, got it. L is 3 for the panel, got it. T infinity on the inside, 4 degrees C. T infinity on the outside, the kitchen, 25 degrees C. H on both surfaces is 5. It's not very big because the air is not moving very fast in your kitchen over your refrigerator. The air is not moving very fast inside the refrigerator over your refrigerated food. So H is pretty small for a problem like this. Okay, keep reading. What's the heat gain per unit surface area? Okay, heat gain per unit surface area. Okay, so find Q double prime, watts per square meter, the heat gain. Okay, let's model it first by electric or by thermal resistances. Start out, let's just start with the hot temperature in your kitchen. T infinity outside. Now, in my finger, now we go through convection to the walls of the refrigerator, the metal wall outside. That's convection, 1 over H outside. Now we go through the metal panel by conduction. That's L panel over K panel. Now we go through the insulation. L insulation over K insulation. Now we go through the metal panel on the inside of the refrigerator. That's L panel over K panel. And finally, we go through convection on the outside to T infinity outside. That should be inside, pardon me. T infinity inside, so 1 over H inside. Okay, there we go. We have all the numbers. Here they are. And by the way, this is looking for this. This is a series connection of resistors. Series connection of resistors. 1, 2, 3, 4, 5 resistors. Okay. If you want to, you can label these temperatures here at these nodes. He didn't ask for them in this problem, so I'm not going to label them. But if somebody asks you, what's the temperature of the metal panel on the inside of the refrigerator? That's the temperature right there. That's between the inside convection and the metal panel. Inside convection and metal. That's right there. Okay. But they didn't ask for that, so I'm not going to do that. All right. So this guy, let's just find Q. Q equal T hot. T hot. Oh, by the way, these guys here. Yeah, 77 and 39. Just so you know, 39 degrees Fahrenheit inside, 77 degrees Fahrenheit on the outside. I'll give you some feel for it. The inside refrigerator is supposed to be around 39 degrees. That's kind of a standard. So most refrigerators are designed to a standard like that to keep food fresh and safe. Okay, so anyway, Q, take hot minus cold, 25 minus 4, divided by the sum of the resistances between my two fingers, R equivalent. Since it's a series connection, R equivalent is just the sum of those 5 resistances. 1 over H outside, 1 over 5. Let's just do the convection. Plus 1 over the inside, 1 over 5. Let's go through the metal panel, LP over KP. Okay, LP is here, 3 millimeters. KP is 60. 3 millimeters divided by 60. 3 millimeters divided by 60. Plus the resistance of the insulation, the thickness of the insulation, 50 millimeters. Divided by K insulation, 0.046. These guys, convection. These guys, metal panel. And let's see what else we've got here. And the insulation. When you do that, the answer comes out to be 14.1. So every square meter of the outside of the refrigerator is losing 14 watts. Multiply it by the surface area of the refrigerator, that's how much heat's coming into the refrigerator from the kitchen. Okay. Somebody says, what's giving us the biggest resistance for the heat to flow from the kitchen into the refrigerator? Well, look at the resistances, okay? A big resistance means it's insulating. Oh yeah, it's big. Kinda big. Negligibly small. Negligibly small. I missed another one. Really small. Could we have neglected those 2 resistances? Oh yeah. If you had experience, you'd say, you know what? Neglect. You know what? That's a metal panel. Neglect. Why can you neglect it? Because the resistance is so small. Why is it so small? Because it's thin and made out of good conducting metal. It's thin, made out of a good conducting metal. That's why you can neglect it. Mm-hmm.
Why don't they make that
a little more insulating, but you know, for what purpose? Cosmetic or for heat transfer? Why try and get, let's say, I'll reduce that by half. Does it affect my answer 1 bit? No, not 1 bit. It wouldn't affect your answer 1 bit. If I double this to 3 zeros and a 2, this answer won't change by probably 1/10 of 1%. So why? Now, is it cheaper? And it comes to economics. Is it cheaper? Maybe. Is it strong enough? If I put my elbow in it, plastic, I gotta be careful. Thin plastic, crack. Stainless steel, it won't. There's a lot of things. Strength, money, thermal analysis, so yeah, there's a lot of reasons why. But yeah, you can play. If you're going to play with something, the biggest bang for the bucks, this guy, he's the biggest bang for the bucks. Find better insulation, might cost more. Is it worth it? I don't know. It changes the motor size. Is it worth it? What's electricity cost? All kinds of things like that go on, So yeah. Just for your own information, let's see what the I did find T inside. I said, what's the inside temperature of the refrigerator wall? So I did say find TI. There's TI. Okay. Okay. There it is, 14.1. I want to find TI. Okay, where is TI? On the inside, it's right here. There's TI. Put your finger between TI and some temperature you know. T infinity I, 4 degrees. Put your finger between the temperature you want to find and what you know. There. You don't like that? Put your finger between two temperatures, or what you want to find, and what you know. That. It gives you the same answer either way. Q equal 25 minus TI divided by these 4 guys, pardon me. Or Q equal TI minus 4 divided by 1 over H, and H was 5. The inside wall of the refrigerator is at 6.82 degrees C. You could find the temperature anywhere I put a check mark. You can find all those temperatures by playing the game like I played it here. Once you find Q, 14.1, I can tell you any of those temperatures by the check mark with the note. Okay, good stopping point. So we'll stop for today. No homework due